All right. So we're going to try this. I'm going to just move this table here, I guess. I'm going to try to use this whiteboard behind me. If you guys in person have any trouble seeing anything, I'll try to write pretty big behind me as we work through this. So what's coming up? Today we should be able to get through binomial examples of binomial distribution. We'll do the Poisson on Wednesday, and then we'll do the uniform on Friday. So that should be kind of the last of the new material. We might even get done a little bit earlier on Friday, and I'll just start kind of going through some of those practice exam problems. Excuse me. And then Monday will be our exam, and I'll talk a little bit more about that probably next class and Friday in terms of exactly the procedure. But you'll have kind of at least a 24-hour kind of window to go on Canvas, take that exam. And then in class on Monday, what we'll use class time for is just to do some more practice problems. If you guys have questions on any of the practice exams, I'll start with those. I might do some problems I think might be helpful for the exam. Sorry, I had something in my throat. All right, so that's kind of where we're going. So let's start talking about the binomial today. So the extra, I taped kind of an extra little recording. It was basically just for regular discrete random variables. It's not anything crazy. It's really very similar to what we were doing when we looked at relative frequencies and did weighted means and weighted variances as well. So it was a lot of stuff that we've kind of already seen, just in a slightly different light. So if you haven't watched that, get on, watch that. If you haven't watched that though, it shouldn't really hinder from today's lecture. So just to kind of show you on Canvas, exam 1 practice materials under the files tab. That's where those practice exams and their answers are, as well as a formula sheet that should have any formula that you would need for that exam. So usually if we took these in person, I'd hand that out. Obviously you can kind of download this and have it open as you're doing the exam next Monday. But here's the materials to kind of start studying for the exam, okay? Any questions for me before we get kind of started here? No? So, kind of part of the discussion in that extra video was we have these variables that we're going to say the outcomes can only be discrete. So this is either going to be integer values or it's going to be a very small subset of potential values we could see. So maybe it's something like you can only see 0, 3, 6, and 9, right? Technically, you can't see every integer, but it's a small subset. There's only 4 possible outcomes you can see. That's going to be a discrete random variable for us. We don't know what the outcome is going to be. Each outcome has a different likelihood of occurring. And what we really want to know is, eventually we'll see today, what's the probability we see each one of those outcomes, right? So we're going to talk about a very specific discrete random variable, which is binomial, right? And these variables, if it fits the criteria I'm about to set out, will always follow this binomial distribution, right? So the first thing we need is we're going to be running some experiment. This could be as simple as flipping a coin, right? We talked about these experiments. They're not like biology experiments. It could be something as simple as flipping a coin, right? So we're going to do this n number of n number of times, and we're going to call these trials, right? So we're going to do the experiment the exact same way every single time, right? Every single time we run the experiment, we can see two possible options. I'm going to call them success and failure. If you want to, you can think about it as 1, 0. If I'm flipping a coin, it would be heads, tails. And the success is going to be kind of whatever the example is. It's what I'm looking for. And then the failure would be I don't see that occur. Right? Every single time we run this experiment, the probability of seeing a success on any one trial is going to be the same. So if I flip a coin, every single time the probability I see a head is 0.5. Right? And we also need our trials to be independent. So if I flip a coin and get a heads on the first one, that doesn't impact the probability that I'm going to see a heads on the second. Right? As long as we have an example that fits this criteria, we know we can use the binomial distribution. Right? So we've got these things. The next question we might want to ask is, okay, if I flip a coin, say 100 times, how many, what's the probability that I see 50 successes? Right? Well, we know excuse me, if it's in like a regular coin, if I flip a coin 100 times, on average, I would see it come up heads about 50 times. But on any 100 coin flips, I might see only 49 heads. I might see 54, right? It's over infinity, we know that it'll be 50%, but if especially if I'm doing not 100, but 10 coin flips, it very well could be that I flip all 10 coins and I get 10 heads, right? Now that's gonna be a lot less likely than if I flip that coin and only see it come up heads 5 times, right? But maybe those are the probabilities I'm interested in. What's the likelihood if I flip this coin 10 times, it comes up heads all 10 times? What's the probability it only comes up heads 4 times? Right? That's what we're gonna be trying to find, okay, what those probabilities are. So if I wanna know this probability mass function, which is essentially gonna tell me what's the probability that I see X number of successes out of my N trials, right? What's the probability I see 6 heads out of 10 coin flips? So that equation is going to look like this. So this is kind of nasty, but we'll walk through it here. It's not, I don't think it's terribly tough once we break it down. So this N is just our number of trials. So it's the number of times we're running the experiment, or in our coin flip example, the number of times I'm flipping my coin. X is the number of successes I'm interested in finding the probability of. So if I want to know what's the probability I get 4 out of 10 coin flips that come up heads, my X would be 4. If I want to know what's the probability I see 9 of those 10 coin flips come up heads, my X would be 9. Okay? So X is our number of successes, N is our number of trials, and then this P is going to be the probability of success on any one trial. So this is going to be like the underlying probability on any one coin flip, which if I have a fair coin, the probability it comes up heads every single time would just be 0.5 here. Okay? So number of successes we're interested in finding the probability of, the number of times we run this experiment or the number of trials, and the probability of success on any one trial. Those are the only 3 things we need. Once we have values for those and we plug everything in, all of these will be numbers, right? In terms of mathematics of this, right, this is just going to take the probability to the power of the number of successes, 1 minus the probability to the power of the number of trials minus the number of successes. And then the only thing left that we might not know is, what does this exclamation point mean in this formula, right? Am I just really excited about the number of trials? No. So this is what we're going to call, once we have this in a formula, this is a factorial, right? So all a factorial means, and I have a slightly kind of more textbook definition, but if I have, say, 5 factorial, is that showing up real well? I can actually make this bigger. Right? If I have 5 factorial, that's just 5 times 4 times 3 times 2 times 1. If I have 10 factorial, 10 times 9 times 8, all the way down to 1, right? So all it means is take the number that's in front of that exclamation point and start multiplying, starting there, and multiply all the way down to 1, okay? A little bit more of a technical definition. Take that value, multiply it by that value minus 1 times that value minus 2. But that's really all I'm doing here, right? I think it's a little bit easier to not see the mathematical formula here and just think I'm multiplying from this number all the way down to 1, okay? So that's what we're going to do, and that should return to us the probability of whatever that number of successes are. So one thing I wanted to make sure I mention here, which is why I added it in here, if I have a 0 factorial is always 1. And then, of course, anything that gets raised to the 0 power will also be 1. Right? So those are 2 kind of important things to remember. Anything to the 0 power is 1, and 0 factorial is 1. So kind of a weird property of these factorials is 0 factorial is actually the same as 1 factorial, right? Because 1 factorial would be 1 times nothing, so it's just 1. But then it's just a property of the binomial that 0 factorial will also treat as 1. Okay? So let's work through an actual example and kind of give some numbers to this, and I'll show you a little bit more about those factorials. Okay? So let's say I have a bias coin. I'm going to flip it 10 times. The probability it comes up heads on any one flip is 0.4. So instead of 0.5 here, it's a bias coin. What's the probability that we get 4 of those 10 coin flips to come up heads? Right? Well, my number of trials would be what here? Just 10. I'm flipping the coin 10 times and running the experiment 10 times. What's the number of successes I'm interested in finding the probability of? Well, I want to know the probability that I get exactly 4 of those 10 to come up heads. And the probability in any one coin flip that it comes up heads is 0.4. So I've got my N, my X, and my P here. Okay. So once I've identified that, it's pretty easy, right? I have my formula. I just start plugging things in. Everywhere I see a n, there's a 10. Everywhere I see x, 4. Everywhere there's a p, 0.4, right? And I just write that formula out with the values for my particular example. Okay? Now, one thing I would do if I'm working on this, I wouldn't try to enter this all in my calculator at once. First of all, there's a lot of parentheses here that I can do this math in my head hopefully pretty easy. 1 minus 0.4 is 0.6. 10 minus 4 is 6, so 0.6 to the 6th. That's a lot easier to get in my calculator than all these parentheses and maybe making a mistake, right? So me personally, that's how I usually try to simplify and do what I can do in my head first. So 0.4 to the 4th times 0.6 to the 6th. I might write that number down, and now I'm going to try to figure out what this guy is right here, right? This fraction of factorials. Okay? So I'll rewrite it here. But what we were looking for was 10 factorial. Let me see where I'm at here. So 10 factorial divided by 4 factorial, 10 minus 4 factorial, which is really just 6 factorial. I can do that math in my head as well. Oop, I probably have to move this for you guys on Zoom, huh? Okay. Well, if I want to rewrite this, right, I can do this in a slightly different way. Now, if I have my calculator for like a TI-84 or 83 or whatever, you should be able to hit math, go over to it's like either PRB or it might just say probability. And under that probability option, you should find that factorial button. So then you should just be able to put 10, math, go over to the PR probability, go down to the exclamation point or factorial, hit it, and it'll be able to do it for you. All right. If you have like not as quite as advanced of a calculator, usually it's like something like hit second math or second, sometimes there's a PRB button on there that you'll find the factorial under. If you're having problems finding it on your calculator, send me an email. We could maybe set a Zoom. I usually can help. If you just tell me the type of calculator, usually through Google search, I can find it pretty easily for you. I've yet to have one that I can't find it on unless it's like a dollar store calculator. Those don't have it in. But yeah, if you make sure you know where that's at on your calculator that you're going to use for the exam on Monday. Okay? Like I said, for the TI-83, 84, should just be under math, go over to probability. Are any of you finding it in here that have it? Yeah, okay. So what happens if you try to do, instead of this example, I'll give you a different one and then we'll come back to this actually. I changed my mind. Let's say I had 100 factorial and I wanted to know 2 successes. What happens if you try to put 100 factorial into your calculator? No one even wants to try for me. It gives you an error message. It tells you, it blows up, right? This is a huge number and your calculator can't handle it. I don't even know how far Excel will go. We could probably play around with it and figure out what its limit is. I think a calculator's is like somewhere in the 60s, right? But if I give you this, it should be pretty easy to find because let's think about what's really going on here. 100 factorial is 100 times 99 times 98 times 97 all the way down to 1. What's in the denominator? 2 times 1. This is 98, right? 100 minus 2. So times 98 times 97 times 96, right? Because it's 98 factorial. All the way down. Well, notice everything past 97 would cancel. Actually, sorry. Everything past 98 would cancel here. So actually, all this means is 100 times 99 divided by 2 times 1. Your calculator can easily handle that. But if you try to enter it in using those factorials, it's going to yell at you because it can't, because at first it's trying to calculate this number and it can't do that, okay? So a lot of times we can simplify these factorials even if you're not comfortable using that factorial button in your calculator. The 10 and 4 one, I could simplify that one down as well, not quite as much, right? So this is like 6 factorial. So you can kind of imagine once I write this out, everything past the 6 will cancel. So I'd be left with that once I cancel everything out past that 6. Right? So it's a little, doesn't save me as much time as it did up here, but we can solve it even without using that factorial button in our calculators. Okay? Any questions on that? I don't know if can you see that okay? All right. Any questions on that? Shouldn't be too bad. So, if we go ahead and we put this in, we'll get about 0.251, right? So it's telling us that If I flip a coin 10 times, the probability I see 4 of them come up heads with this biased coin is about 25%, or the probability of 0.25. Right? So we'll kind of revisit this here in just a second. But let's do a slightly different example where it's not just as easy as a coin flip, and it's kind of a, how do we define the success? So here I've got an example where I say, okay, there's some report that says 30% of all adults have a 4-year college degree. So if I was to choose one person at random, the probability they have a college degree would be 0.3, right? Just one person at random. If I randomly select 5 people, right, 5 adults here, what's the probability that 3 of them have a degree? So here, my experiment is really just randomly selecting a person and asking them a question. So what's my number of trials here? 5. I'm asking 5 people. The number of successes I'm interested in is 3. X is 3. And my probability of success for any one person would be 0.3, because here, my success is that they have a college degree, right? And then I guess the failure would be that they don't. That's not necessarily true, but the way in which we're constructing this example. Right? So we're looking for this probability that X is equal to 3. We've already identified our number of trials, our number of successes, and our probability of success. From here, it's just a matter of taking that formula and plugging in all our values. I mean, it's as easy as that. Once we've identified those 3 pieces of information, it's really just being able to use this formula correctly, right? Plugging our values in and being able to get entered into our calculator, okay? Any questions on that one before we keep moving? I'm gonna show you something here in a second too. But before I move on, I wanna make sure we're okay with that. Let me double check, make sure the chat's okay. All right. So we get about a probability of 0.13 here. Okay. I think the next one is one where I see what's the probability of that 4. Okay. So what's the only thing that would change in this example? I still have asking the same people about the same thing. I'm still selecting 5, but now I want to know what's the probability that 4 of them have a college degree. What's the only thing that changes there? My N is still 5. My P is still 0.3. It's just now my number of successes I'm interested in is 4, right? X is equal to 4. So it'll be the exact same thing, but I put a 4 in here for X. Now let's take a step back and think about this. If I have 5 people, actually we'll change the numbers so it's a little bit easier. If I had 10 people and the probability that any one person has a college degree is 0.3, on average, how many people out of those 10 would have a college degree? 3, right? So in your head, what you did intuitively there was you said, I've got N number of trials, I'll multiply that by the probability of success, and that should tell me like the expected value. So I'm leading it into some stuff we'll talk about later, but essentially the mean of the binomial. And that kind of seems intuitive, right? You didn't have to have a formula to do that in your head. You said, okay, if 30% of people have degrees, if I looked at 10 people, on average, about 3 of them would have it. So that should be the most likely outcome, right? Now, if I'm thinking about 5, right, how many should we expect out of 5? Well, it's 1.5. So the most common outcomes we would see there would be like 1 and 2, right? Because you can't see 1.5 people. We'd have to either see 1 or 2. But if we think about it, as I move further away from that expected value, we'll keep the number at 10 again, just to make it easier to think about. So 3 is the expected number of people out of 10. What do you think is true about the probability of seeing 3 people out of 10 have a degree, as opposed to seeing all 10 of 10 have a degree? That probability of seeing 3 is probably greater, right? I mean, if I'm thinking about all 10 people having a college degree, that probability is probably relatively low, right? And so as I move away from that expected value, the probabilities decline, right? The probability I see 5 people have a college degree is higher than the probability I see 6, which is higher than the probability I see 7 and 8 and 9 and 10, because it's just moving away further and further from that expected value. Okay? So here, if we have 5 people, and I know that my expected value is about 1.5, well, when I found the probability of 3 was 0.13, seeing 4 out of the 5 people have a degree is even less likely. So automatically, I know my probability has to be lower than that 0.13. All right? So as I move further and further away from kind of that intuitive expected value, the probabilities of seeing those number of successes start to decline. I put this in the context of flipping a coin. You would expect if I flip a coin 100 times, it comes up heads on average 50 times. So the probability of seeing 50 is going to be the most likely outcome. It's going to be the highest probability of all the possible outcomes. Then I start to say, well, what's the probability I see 60 out of the 100? Well, it's less likely than seeing 50. Well, what's the probability I see 70 out of the 100? Well, it's less likely than 60. What's the probability I see 80, right? As I move to seeing all of the coin flips come up heads, I know that that's just going to become more and more unlikely, right? And it's the same idea here, right? It's not quite as easy to think about because the probability isn't exactly 0.5, and I'm not talking about 100, exactly 100 number of trials, but it's the same idea. As I move away from that expected value, the probability of those number of successes starts to decline. So here, this was 0.13, the probability I see not 3 out of 5, but 4 out of 5, I know is going to be lower, right? Because it's further from that expected value of 1.5. Right? Does that intuitively, does it kind of make sense? Or is there any questions on that? We're okay with that line of thinking? Okay. But we can actually, let's say here I only gave you one option that was less than 0.13, so we know this is the answer. But if I wanted to actually compute this, right, if I gave you a bunch of answers that were lower than 0.13, it's the exact same thing we did before. Number of trials 5, probability of success 0.3. But now our x is 4. Just plug everything in. It's a matter of getting comfortable using your calculator for this binomial. Okay. Now notice, if I wanted to simplify this, what could I simplify this down to? So this is going to be 5 times 4 times 3 times 2 times 1. This is going to be 4 times 3 times 2 times 1. So everything there would cancel except for the 5. And then what would this be? Well, 5 minus 4 is 1. 1 factorial is 1. So this is actually just 5 divided by 1, or 5. Right? So this is one of those ones where if I just think about it and I write it out, very quickly I can see I don't even need to use my calculator for this one. And I can see that everything cancels and all I'm left with is that 5. Okay? And then it's just being able to put powers into your calculator, which I'm assuming most of you are probably okay with. Okay? So we get a pretty low probability here, right? Now, what if I wanted to find the probability that all 5 had a college degree? What do you think is probably true about that probability? It's even lower. It's probably pretty much 0. We could plug in 5 here and figure it out, but it's going to be really close to 0, right? If the probability from 3 to 4 fell by 0.13 to 0.028, I'm guessing once we go from 4 to 5, it's going to it's going to be almost 0 once we put that in. Okay. And so sometimes, like on an exam, or if I do an online quiz question, sometimes maybe the answer would be approximately 0, right? If it's 0.0004, I'm not going to put that as a possible answer. I'm going to put approximately 0, right, if I'm out 4 or 5 decimal points. Okay. All right. What if instead I wanted to do something like, what's the probability that at least 3 out of the 5 have a college degree? So what am I really saying with the probability of at least 3 out of 5? What I'm really saying is, what's the probability that this x value is greater than or equal to 3, right? At least 3. It could be 3, it could be 4, it could be 5. Now, when I ask people this, I either see that exactly 3 out of 5 have a degree, or I see exactly 4 out of 5 have a degree, or I see all 5 out of 5, right? I see one of those different outcomes. And so because there's no overlap in those, what I'm really saying is, well, the probability of seeing 3 or higher is really just the probability of 3 plus the probability of 4 plus the probability of 5. There's no values I can see in between. So this is really just what outcomes fit this criteria and then add up the probability of all those outcomes. So what fits this criteria? Well, that is not what I meant to do. X is equal to 3 plus the probability that x is equal to 4 plus the probability x is equal to 5, right? I'm just adding up the probability of all the possible outcomes that fit this criteria. Oops, for those on Zoom, you should be yelling at me right now. Here, I'll actually go here. Right? So once we know we want the probability that x is greater than or equal to 3, it's just add up the probabilities of all the outcomes that fit that criteria. Okay? Now, we've already actually found these two, right? This was what, 0.13, 0.028. and this one's going to be so close to 0. You just almost think of it as 0. So if I add these up, I'm going to get about what? Looks like 0.15a, so about 0.16. I don't know the exact, I'm rounding here in my head, and I think I've got it on the slide here in just a second, but that's the general idea of what we're doing there. Now, what if I wanted the probability x is less than 3? There's 2 ways I could think about finding this. Yeah, so the easy way, well, especially if we already had this work done, the easy way is, well, if I think about this as event A, what would A complement be? Just being less than 3, right? What do I know is true about the probability of an event and its complement? They have to add up to 1. So if I know this one, to find the other guy, I could just subtract that from 1, right? This is event A. So if I subtract the probability of A from 1, I would get the probability of the complement. Right? If I didn't have this already done, what's another way I could find this? Well, what fits that criteria of being less than 3? The only outcomes we could see would be 0, 1, 2. Not 3, because it doesn't have the equality, right? So there, another way to find this would be take the probability x is equal to 0, add that to the probability x is equal to 1, add that to the probability x is equal to 2, right? Kind of similar to what we did here. Whatever fits the criteria, just find the probability of each outcome and then add them up. Okay? Now, sometimes, so any questions on that before I keep going? Because I'm going to erase some of this. So if you have any questions on any of this, let me know. Let me see, I'll just pop the chat up over here. Okay. So this comes in handy using this complement rule in other scenarios a little bit more so, right? So let's say I wanted, let's say I did that one where I had like 100 trials and I wanted to know the probability of 2 successes or something. So let's say I've got 100 trials and I want the probability x is greater than or equal to 2. Well, if I have 100 trials, what fits this criteria? X could be 2, X could be 3, 4, 5, 6. And to find each one of those probabilities, I have to use that binomial equation. So I'm going to be using it, what, 99 times, right? I don't want to do that, right? Or right, 98 times, right? That's insane, right? I don't have that much time. But if I think about this as event A, then I know it's also equal to 1 minus A complement, which what's A complement here? X just being less than 2. What outcomes fit this criteria? 0 and 1. I only have to use that equation twice, right? So it can save me a lot of time, especially when I have examples like this where I'm looking for, is it greater than or equal to, going from a small number to a really, really large number. If I just rewrite that as 1 minus the complement, that's a lot more manageable, right? So you almost think about this would be like 1 minus the probability x is equal to 0 plus the probability x is equal to 1. Okay. Any questions on that for keep going? And so a lot of this is just going to be kind of working through some of these binomial equations on your own, getting comfortable using your calculator to reproduce the answers. I can put up, you have the practice exams. I have another homework that I can put up that's just like, will be like additional practice problems for some of this probability stuff. So I'll get that posted. It's not going to be for points. You don't have to do it. It's just going to be another thing that'll be out there if you do kind of want some more practice, especially with this binomial and Poisson examples, okay? All right. No other questions? So I kind of already went through all this on the board, but right, I can rewrite this as probability of 3 plus 4 plus 5, or 1 minus the complement. Either way, kind of gets me the same answer. If I go ahead and I do this, we already talked about finding these two. The probability x is equal to 5. I said it's approximately 0. Apparently, it's a little bit higher than I thought. It's 0.002, right? So we could get it out to the third digit there, I guess, if we really wanted to. You posting? So the extra practice will be like, it'll look like a Connect homework. So if you submit it, you should be able to see kind of you can do the check my work, and I'll have it set so that you can actually see what the answers are. Right? So we would add these all up. we get about 0.162, which is what I kind of said before, about 0.16. Okay. So no questions on this? Okay with this kind of binomial stuff for now? All right. So I'm going to kind of alluded to this earlier, but the summary statistics for the binomial are always going to follow the same formula. So for the mean, it'll always be n times p. So your number of trials times the probability of success. This is the one that we said is really intuitive, especially when I have easy numbers. If I have 100 coin flips, and I know that on any coin flip that comes up heads 0.5, the expected number of flips out of 100 that I'll see should be 50. Right? Or out of 10 people, if the probability any one person has a college degree is 0.3, the expected number out of 10 that have a degree would be 3. Well, how did I get those? 0.3 times 10 gave me the 3. 0.5 times 100 gave me the 50. Right? So it's kind of intuitive, but here's the actual formula that will work for us. The variance isn't quite as intuitive. You can walk through the mathematical proof if you want to, but you can imagine if I have all these different possible outcomes and I subtract the mean and square it, you can walk through the mathematical proof and show, as long as it's a binomial distribution, that you have the success failure, the only outcomes you can see on any one trial. It'll always boil down to that the variance is, no matter what the number of trials is, no matter the probability of success, this will always be the variance as well. Right? So these are our two equations for the mean and the variance. And if I want the standard deviation, just like always, what's the only thing I have to do? Take the square root of the variance, right? Now, once I have this mean, I know that it's the most likely outcome. It's the expected value, right? So whatever value this mean is, that will be the value that has the highest probability of occurring, right? If I think about the coin flip, if I flip a coin 100 times, the most common outcome I will see is that 50 of the 100 come up heads. Now, sometimes I'll see 49 or 51, but those will have a lower probability than seeing that expected value or that mean of 50. Right? So if I think about this, let me see. Yeah, we got some nice visuals here. So I'll use this, and I might do some board work here in a second. So if I had a binomial example where n is 5 and the probability of success is 1, what's my expected value there? 5 times 0.1. So my expected value is 0.5. So the most likely outcomes should be, if I end up with a non-integer, the values on either side of my expected value. So if my expected value or my mean is 0.5, the most likely outcomes are 0 and 1. Okay? And then as I move away from that expected value to higher numbers of successes, notice those probabilities start to decline. If I have a binomial where n is 5 and the probability of success is 0.5, my expected value there is 5 times 0.5, so 2.5. So 2 and 3 are going to be the most likely outcomes. And as I move in either direction to a smaller number of successes or a larger number of successes away from that expected value or that mean, the probabilities decline. Okay? N is 5, probability of success is 0.9. Now it's just that, it's the exact same thing before, but now our expected value is 4.5. So 4 and 5 are the most likely. And as we move away from those values, the probability of success falls. Okay? And you can imagine if we start to increase the n, the number of trials, well, if I only run this experiment 5 times, I can only see 0 through 5 as the number of successes. If I run it 50 times, I can see 0 through 50 be the possible number of successes. So here, if n was 50, probability of success is 0.5. My expected value or my mean would be n times p, so 50 times 0.5 or 25. And then as I move in either direction, things become less and less likely. And when I have more options, think about it this way. Even if everything was equally as likely, if I had 10 possible outcomes, then everything would have a probability of 1/10. If I go to 100 possible outcomes, everything would be 1 over 100. So just including more possible outcomes when I have a higher number of trials will kind of reduce the probability of everything, right? Notice here, the most likely outcome had a probability of occurring of about 0.12 or something. When I only had 5 possible outcomes, the most likely outcome had a probability of occurring of 0.6, right? So having a higher number of trials, adding in a higher number of possible successes, just kind of reduces the probability I could see for every possible outcome. Right? But same kind of story. As I move away from that expected value, the probabilities decline. Yeah?
I have a question about, so like in the first one, it says that the number of trials is 5, that's probability 0.1.
Yep.
So your value be 0.5.
Mm-hmm.
So
Why is 0 and 1 not equally as likely? So if you look, so if we looked at, if you think about an actual like binomial formula, whenever it's skewed, so look at these guys, right? So when my probability of success is low, 0.1 or 0.2, it's always going to be that my data is kind of this right skewed data, right? Notice it has like long right tails. So why aren't these exactly the same? How's a good way I can describe this? Because the expected value is a mean, it's going to be influenced by the fact that you have, okay, so my expected value is 0.5, right? How many possible outcomes are to the left of that? 1. How many possible outcomes are to the right? 4. So those values of like 4 and 5 are pulling that expected value up to 0.5. So it's not going to be that 0.5 is like, it's almost like the same thing we talked about, the mean gets influenced by these extremely large values. They're not extremely large here, but there are just more values possible on that right-hand side. And so they kind of pull that mean up, even though if we looked at like the count, the most common outcome we would see, the most common outcome would be 0, right? But there's just more values on the other side that are pulling that mean or expected value up. Does that kind of answer? Yeah. Yeah, so I mean, it's kind of weird with these smaller ones too, that, you know, there's only one value to the left, and so the difference is way more pronounced. If you look here, like the expected value on 20 and 0.2 would be 4, but notice, even though that's the most common value, 3 is also not very far behind it. And it's because, right, the expected value is being pulled up to 4 because there's so many more possible outcomes to the right there. Yeah. That's a good question, actually. Not that all of you don't have great questions, but like that one particular was a good question, because it's hard to think. It is always weird looking at that and thinking about, well, if I'm smack dab in the middle, why the hell aren't they the same probability, right? And it's because they're being pulled. Notice this one. Here, the expected value is 2.5. There was equal number of outcomes on either side, and so 2 and 3 were equally as likely. Yeah. All right, good question. Any other questions on that before we keep moving? All right. So, you know, hopefully it would be a relatively easy, if I gave you a question to find the mean and the variance of a binomial example, I mean, hopefully it's relatively easy. We'll use that same college one. My N is 5, right? 5 people. My probability of success is 0.3. So 1.5 was the expected value. We kind of already talked about that. And then how do I find the variance? Well, it's just N times P times 1 minus P. So 5 times 0.3 times 1 minus 0.3, which I think gives us 1.05. Right? And if I wanted the standard deviation there, the only other thing I'd have to do is take the square root of that. Right? So those should be pretty easy, I think. Those are relatively easy. There we go. I might skip this because I feel like I usually just like, I am going to skip this. Usually there's just like, confuses people more than it makes things kind of connect. But you can think of the binomial, it is a special case of discrete random variables. So if you go back in the extra video and watch, and we think, well, we have all these different possible outcomes and their associated probabilities, or kind of like their weights, you could actually think about breaking this down for any one given trial. The probability of success, right? You either see a 0 or 1, and the probability that you see a 1 is whatever the probability of success is. The probability you see a 0 is 1 minus that. You could treat this just like a regular discrete random variable and find the mean the exact same way. So this is, I don't know. Like I said, sometimes I just feel like this complicates things even more. So let's just not worry about this. So same thing's true for the variance, but let's just not worry about it. I think it just makes things a little more complicated. So let's talk about situations where we can use the binomial. So let's say I want to, so actually, sorry, we're looking for which one does not fit the binomial here, right? So let's say the first one we have is calculate the expected number of coin flips that come up heads in 123 flips. Well, this sounds a lot like what we're doing, right? Our number of trials here would be 123. If we had the probability, if it's just a regular coin, the probability of success is 0.5. To find the expected number, or expected value, that's just the mean, right? When we're talking about a variable, a random variable, and it has uncertainty in the outcome, we kind of use that word as the mean of this random variable and expected value interchangeably. They mean the same thing, right? It's the mean, but to be more specific, it's the expected value because it's something that hasn't occurred yet. We're using probabilities to like almost predict the future, right? A future outcome. So this one would be a really good one, right? Because success, failure, we can only see a head or a tails come up. What about calculating the probability that at least 5 out of 20 patients will get nauseous from an antibiotic? As long as all patients are equally as likely to react to this antibiotic, right? The probability they get sick from this antibiotic is the same across all patients. We would have 20 trials. Number of successes we're interested in is 5 or more, so probably x is greater than or equal to 5. So we have our x, n, and if that underlying probability of success, here it's weird because success is getting sick from this antibiotic, but if that probability is the same across all people, we actually have a good example here. Calculating the probability that an air traffic controller at the Muncie airport makes at least 3 errors per week. So this is one that we'll talk a little bit more on Wednesday. I might introduce it before we end the class, but so I'm thinking about what would my number of trials be here? Well, I said per week, but is my n how many people are landing planes, right? My n shouldn't just be like 7 days or 1 week. If I'm thinking about the number of errors they make, this x, right, should be out of n trials, but I need to know how many times is there something landing that they can make an error on. So if we leave something open-ended with like time, or we give an interval, that's actually going to be what we'll learn is a Poisson distribution instead of a binomial. So anytime you see kind of a time interval, you should be thinking this is not one where I can use the binomial. It's actually going to be something where I need to use that Poisson distribution. And it's very similar, but it's a little bit different since we don't have kind of it capped out, right? Technically, I could make, I don't know how many errors I can make per week unless I have more information about how many people are landing every single day. So calculating the probability that out of 5 customers, exactly 3 make a purchase. Well, if once someone enters a store, everyone's equally as likely to make a purchase, or maybe I'm just thinking about like impulse items, right? A company might be interested in that. I've got 5 customers, that's my number of trials. The X I'm interested in is 3. If I have that underlying probability of success that someone bought something when they walk into a store, I'd have everything I need to do a binomial, right? Because someone either buys something or they don't, so success, failure. All right, so this would be another good one where we could use the binomial. So the only one that doesn't work is this one that has kind of a given time interval and not a capped number of possible successes we could see. All right. Any questions on that or anything about the binomial before we keep moving here? Okay with that? Okay. So instead of doing the Poisson today, I'll do the Poisson Wednesday. We can actually do binomials in Excel pretty easily to avoid kind of using those factorials on our calculator. So here's kind of how we do it, but I'll just show you in Excel just to make it a little bit easier. Yep. So if you can get comfortable using the binomial. Now, if you're not comfortable using the binomial and you put things into Excel wrong, you're going to get some really weird answers with this binomial. But I'll show you if you make a mistake. But yeah, if you're comfortable using it. So we're just going to use this binom.dist formula. Oh, we're going to in a second. Hold on. Let me zoom in here. So binom.dist. Right. Now I can put the numbers in here that I want. So the one I did here was Detroit foreclosures. So I think what I said was, so let's say we're looking at, the first thing we want to put is the number of successes we're interested in. So let's say, what's the probability that exactly 5, right? So 5 is the number of successes I'm interested in. Number of trials, I'm looking at 100 households. The probability that any one home is foreclosed is 4.7%, so 0.47 as a probability. And then this cumulative guy, cumulative means we'll actually be finding the probability that it's 5 or anything below that. So actually, I only want the probability of exactly 5, so I'm going to put a 0 in there. So number of successes, number of trials, probability of success, and this cumulative, if you want the probability of exactly one number, that cumulative you'll put a 0. Okay? And I'll show you if we didn't want exactly one number, what it would look like here in just a second. But if I enter it in like that, right, and hit enter, it'll tell me the probability that exactly 5 households are in foreclosure. So the way that I'm actually going to set this up is I'm always going to be looking at 100 houses. The probability that they're foreclosed will always be the same. And then I can play around with this x value. For now, I want it to be 5, right? So instead of entering the values in here, what I'm going to do is say, well, the first thing I want is the number of successes. That's my x. Second thing is the number of trials. That's right here. That's 100. The third thing was that probability of success, 0.047. And then 0, kind of that last thing, is not cumulative. Right? 0 means it's not cumulative. Sure enough, I get the same answer. I've just used cell references. And now, if I put it what would be the expected number of foreclosures here? Number of trials is 100. Probability of success is 0.047. So 4.7 homes, right? 100 times 0.047, n times p. So if instead of 5, I put in 6, what should be true about the probability of 6 relative to seeing 5 homes foreclosed? Yeah, I'm moving further away from that expected value of 4.7. So sure enough, it gets lower. And I could even prove this to myself, right? Well, 7 gets even lower, 8 gets even lower, 9 gets even lower, right? You can imagine if I wanted to do this, I could set this up in some way in Excel where I built like a column of all the possible x's and then put this next to it, but like froze the number of trials and probability of success. And I could create like gigantic tables that gave me all the probabilities, or I could just have it reference this one cell and kind of play around with it. Right? So it's that easy to do kind of this binomial in Excel. Now, what if I wanted the probability of, what do I have here? More than 8. So this one's a little tricky. Let's say I want the probability of seeing more than 8 homes foreclosed. So I'll put my 8 in here. So I'll use that binom.dist. The number of successes I want to see would be 8. Number of trials, 100. Probability of success. But here, if I put 0 for cumulative, it'll give me exactly 8. If I put a 1 in, what's it going to find the probability of? It's going to find the probability that I see 8 plus the probability of 7 plus the probability of 6 all the way down to 0. Now, that'd be fine, right, if what I wanted was the probability of seeing less than 8, but I wanted more than 8. This tells me the probability that's less than or equal to 8. So what's the only other thing I have to do? Yeah, if this is A, event A is being if event A was being less than or equal to 8, because that's what the cumulative always does. It always says, is it less than or equal to this value? All right? Then the only thing I have to do to find the complement of that is 1 minus that. And that would tell me the probability it's greater than 8. So I can play around with that binomial function. That 1 as the last thing always says find the probability of this number or anything below it. And then I put a 0 in that last number, it finds a probability of exactly whatever number of successes you're telling. Okay? So that's how we can use Excel to kind of make our life a little bit easier with binomials. We'll do the Poisson distribution on Wednesday. I'll leave Zoom open here. If there's any last minute questions, you can kind of talk or chat or come up to me after class. And I'll see you guys on Wednesday.